This module, BIM and Environmental Impact Integration, Planning Tools and Practices, explores how building information modeling, BIM, supports evidence-based environmental decision-making throughout the planning and design phases of a project. By focusing on widely used analytical tools, such as Autodesk Insight, Green Building Studio, One-Click LCA, Tally, Ladybug/Honeybee, and the workflows that connect them, the lecture demonstrates how BIM acts as a central data environment for sustainable design. As cities and buildings increasingly aim for carbon reduction, resilience, and energy efficiency, BIM becomes not only a documentation platform, but also an active planning instrument that guides design teams from concept mapping to post-occupancy monitoring. This lecture is organized into interconnected themes that reflect real environmental planning processes. After introducing the role of BIM in sustainability, the module reviews key simulation tools and LCA platforms commonly used in architectural, engineering, and planning workflows. Subsequent sections examine data exchange formats, material databases, and recommended workflow sequencing, from early-phase modeling to multi-objective optimization. The lecture also emphasizes certification integration, urban-scale planning connections, dashboarding strategies, and digital twin applications. Finally, 2 case studies illustrate the practical benefits of BIM-based environmental assessment. The learning objectives of this course focus on expanding students' capacities to combine BIM with environmental performance evaluation. By the end of the module, learners will be able to identify essential software tools, understand how BIM data structures support simulations, and evaluate planning workflows for carbon, energy, and comfort optimization. They will also understand how BIM outputs contribute to planning frameworks, certification systems, and post-occupancy evaluation. Ultimately, the objective is to demonstrate how BIM-centered planning can produce transparent, measurable, and verifiable environmental outcomes in real projects. BIM supports environmental planning by providing a structured environment where geometric information, material descriptions, and performance properties are stored in an interconnected model. Instead of treating environmental analysis as a separate or late-stage process, BIM enables continuous evaluation throughout the project timeline. When paired with simulation engines, LCA platforms, or optimization tools, BIM becomes a dynamic working space where designers test multiple alternatives and receive immediate feedback on energy use, carbon emissions, daylight availability, and comfort. This integration allows sustainable design principles to influence early decisions where their impact is greatest. The ecosystem of environmental tools connected to BIM covers a wide range of performance categories. Autodesk Insight and Green Building Studio support early-stage and whole building energy analysis. One-Click LCA and Tally provide material-specific embodied carbon assessments directly linked to BIM element quantities. The Ladybug/Honeybee suite offers parametric climate-based analyses, including radiation, daylight, thermal comfort, and environmental optimization. Together, these tools represent a comprehensive digital workflow that supports decision-making across scales, from individual components to entire districts. Autodesk Insight integrates with Revit to provide energy modeling outputs based on geometry, envelope characteristics, mechanical systems, and climate data. It is designed for rapid scenario testing, allowing users to adjust glazing ratios, insulation levels, shading devices, and HVAC efficiencies to evaluate their impact on UE, energy use intensity. Insight also includes solar and daylighting tools that inform passive design strategies. Because it operates at early design stages, Insight helps teams make impactful decisions before architectural details become locked in. Green Building Studio extends BIM-based analysis through cloud-powered simulations that import GBXML exports from Revit or other BIM tools. GBS supports LEED compliance by assessing energy performance, renewable energy contribution, and mechanical system efficiency. It evaluates whole building performance under various climate conditions and mechanical configurations, enabling users to compare design alternatives at the planning stage. This tool is particularly valuable for large-scale developments, feasibility studies, and energy code compliance planning. One-Click LCA is one of the most comprehensive whole-life carbon assessment platforms. It connects to BIM through IFC, Revit plugins, or Excel-based quantity imports. One-Click LCA maps BIM materials to verified EPDs and calculates embodied carbon for all life cycle stages defined by N15978. The platform also includes benchmarks and certification-ready reports, making it valuable for projects pursuing LEED, BREEAM, DGNB, or national carbon regulations. Because it provides region-specific material datasets, it supports realistic carbon accounting. Tally is a Revit-integrated LCA tool developed to allow material-level impact calculations inside BIM environments. By linking each Revit object to environmental datasets during modeling, Tally quantifies embodied carbon, global warming potential, and other impact categories in real time. This supports rapid comparison of design alternatives, for example, substituting insulation materials, altering structural systems, or adjusting facade assemblies. Tally's advantage lies in its seamless integration, enabling designers to make informed environmental decisions without exporting their models to third-party tools. Ladybug and Honeybee, built on the Grasshopper platform, enable parametric climate-based simulations using EPW weather files and radiance, or Energy Plus engines. These tools provide highly customizable analyzers for daylight, thermal comfort, solar radiation, and microclimate conditions. Their parametric nature allows planners to explore thousands of design variations, making them ideal for early-stage optimization or urban-scale planning tasks. They bridge the gap between environmental science and architectural geometry by visualizing performance patterns directly on building or district models. Interoperability is essential for connecting BIM models with specialized environmental tools. IFC enables rich data transfer, including geometry, material assignments, property sets, and classification codes. GPXML supports energy modeling by translating BIM geometry into simplified thermal zone representations compatible with simulation engines. CityGML enables urban-scale environmental modeling by representing terrain, buildings, vegetation, and infrastructure in a structured, semantic format. These formats prevent data loss and ensure consistent environmental evaluation across platforms. Environmental Product Declarations, EPDs, and lifecycle databases such as EC3, Ecological, and ICE play a crucial role in carbon accounting. By linking BIM objects to specific EPDs, designers replace generic assumptions with verified data reflecting real manufacturing processes and supply chains. This integration is vital for accurate embodied carbon assessments. Many planning tools allow automatic matching between BIM material codes and EPD entries, improving the reliability and transparency of carbon calculations. Environmental planning workflows typically follow a structured sequence that begins with conceptual massing and proceeds through iterative simulations. Early phase testing informs envelope characteristics, shading strategies, and massing geometry. Material selection occurs alongside LCA calculations, enabling designers to evaluate embodied carbon before detailed specifications are finalized. Later stages integrate multi-objective optimization, certification documentation, and eventually post-occupancy validation. This sequential approach ensures that environmental considerations guide every major planning decision. Early phase planning has disproportionate influence on environmental performance because decisions on massing, orientation, and envelope form significantly affect heating, cooling, and daylight potential. BIM-based early modeling allows rapid exploration of alternatives, generating performance indicators such as solar access, shading patterns, and preliminary UE estimates. Adjustments made at this stage, like rotating the building mass or altering window placement, can reduce long-term carbon and energy loads more effectively than late-stage interventions. Optimal planning involves balancing multiple environmental objectives, including reducing embodied carbon, minimizing operational energy use, and ensuring occupant comfort. BIM data supports this by providing accurate quantities, surface areas, and thermal properties for simulation. Tools like Insight and Ladybug allow parametric adjustment of envelope parameters, while LCA platforms quantify carbon impacts for chosen materials. Multi-objective optimization frameworks integrate these datasets to generate design solutions that meet environmental, functional, and cost constraints simultaneously. Green building certifications require structured documentation of material impacts, daylight performance, energy modeling, and carbon analysis, all of which can be generated from BIM-based tools. Automated BIM workflows extract material quantities for lead material and resources, MR credits, validate daylighting for I credits, and produce energy modeling results required for lead E credits or BREEAM's energy and materials categories. Dashboards and automated reports streamline certification processes and reduce administrative workload for planning teams. At the urban scale, BIM collaborates with GIS and microclimate tools to assess outdoor comfort, solar access, wind flow, and heat island effects. Ladybug's radiation and comfort maps help evaluate street canyons, open spaces, and building clusters. City GML models support district energy planning and renewable potential mapping. By integrating BIM geometry into these workflows, urban planners can ensure that environmental logic, such as shading strategies or passive cooling, extends beyond individual buildings into the broader urban fabric. Dashboards transform complex simulation results into accessible visuals, such as carbon charts, energy use graphs, and scenario comparisons. These interfaces help stakeholders understand trade-offs, prioritize interventions, and track progress. Many platforms integrate with BIM to automatically retrieve updated quantities and performance data. Dashboards are particularly valuable for communicating with clients, regulatory agencies, or certification bodies, ensuring transparency and accountability during the planning process. Post-occupancy evaluation, POE, verifies whether real building performance aligns with design stage predictions. BIM models evolve into digital twins by linking real-time sensor data, such as temperature, air quality, energy use, and occupancy patterns, to the building model. Digital twins help identify performance gaps, support operational carbon monitoring, and inform future retrofit strategies. This creates a feedback loop where lessons learned from operating buildings guide subsequent planning processes. In one example, a design team used Revit and Tally to evaluate the embodied carbon of multiple facade assemblies. By adjusting the insulation type, reducing aluminum framing, and implementing bio-based cladding materials, the team achieved a 22% reduction in embodied carbon without compromising performance or aesthetics. The ability to test scenarios directly in BIM accelerated the decision-making process and facilitated transparent communication with clients and regulatory authorities. A second case involved massing studies conducted with Autodesk Insight for a high-performance office building. Several geometry variations were tested, adjusting orientation, floor depth, glazing distribution, and shading devices. The final design achieved an 18% improvement in UE over the baseline model. Envelope refinements and PV sizing strategies were later incorporated into detailed simulations, demonstrating a smooth transition from concept stage modeling to advanced energy analysis. This module demonstrated that planning workflows combining BIM with environmental tools create an integrated, transparent, and data-driven design process. By connecting geometry, materials, simulations, and reporting mechanisms, BIM ensures that sustainability objectives influence decisions from the earliest concept phase to post-occupancy evaluation. Tools like Insight, GBS, Tally, and Ladybug enable iterative and evidence-based optimization, while interoperability standards and dashboards ensure that results are accurate, shareable, and actionable.